Welcome. Let us consider the quantity which is known as a quadric. Okay. So, it is defined as follows: Sij xi xj is equal to 1. Okay. We are using Einstein's summation convention. Suppose if I and j run from 1 to 3. So, what is this quantity expanded? It is nothing but S1 1 x1 squared plus S2 2 x2 squared plus S3 3 x3 squared plus S12 2S12 x1 x2 plus 2S13 x1 x3 plus 2 S23 x2 x3 is equal to 1. So, this is the generic representation of a geometric object, which if all these 1 1 2 2 3 3 etc. are real, basically is an ellipsoid, right. So, we have already seen this. We have said that first rank tensors are those quantities which transform like the position vector of any point. Second rank tensors are those quantities which transform like the multiplication of the pairs of points, right. Now, if you look at the representation quadric xi xj, suppose if I did a coordinate transformation and I went to xi prime xj prime. So, they will I will have some a 2 a's multiplying Sij, that will be equal to Sij prime. So, this S basically transforms like a second rank tensor, but notice because when I multiply xi xj, x1 x2 and x2 x1 is the same. So, that is why I have a 2 here. The quadric written in this fashion transforms exactly like a symmetric second rank tensor. Because this quadric transforms like a symmetric second rank tensor, this is known as representation quadric for, so this is nothing but representation quadric for a symmetric second rank tensor. Okay. Now, a general property of such a quadric is that you can always find 3 directions in which if you write all this. So, then all these cross terms will go away and you will get S1 x1 squared plus S2 x2 squared plus S3 x3 squared equal to 1. Okay. This can always be transformed by choosing appropriate x1, x2, x3 in this form, where x1, x2, x3 will be perpendicular to each other. So, what this means is that this can always be represented as an ellipsoid, right, which is like that. So, what is this S1? So, it is nothing but the 1 by square root of this half distance, right. So, you have an ellipse, for example, the semi major semi minor axis. So, this is an ellipsoid. So, it has 3 S1, S2, S3, 3 perpendicular axes. So, basically S1 is 1 by, so 1 by square root of S1 is nothing but the A, right. So, this if you compare with x1 squared by a squared plus x2 squared by b squared plus x3 squared by c squared equal to 1, which is the equation of such an ellipsoid. So, you can identify S1 with 1 by a is nothing but 1 by square root of S1, b is nothing but 1 by square root of S2, c is nothing but 1 by square root of S3. In other words, the symmetric second rank tensor transforms like this quadric, and a property of the quadric is that it can always be represented in the form of an ellipsoid like this. Now, all symmetric second rank tensors have this representation. If you consider now in a cubic crystal, you have the symmetric second rank tensor, namely diffusivity. So, the diffusivity, if you want to represent as a quadric, you realize that because there should be 4 3-fold axis. And if you try to manage 4 3-fold axis on a generic ellipsoid like that, it will become a sphere. This is the only way, unless the representation quadric for a symmetric second rank tensor is a sphere, it cannot have 4 3-fold axis, and 4 3-fold axis is essential if that symmetric second rank tensor is a material property of the cubic crystal, which automatically implies, because it is a sphere, now S1, S2, S3 are all the same, which automatically implies that your symmetric second rank tensor in cubic system has become isotropic, or it has only one. So, instead of all these 3 half axes, you have the radius of the sphere as the only independent quantity. Okay. So, this is basically the same information as we argued out using the earlier argument, where we tried to take the define the symmetry of a given crystal property. That we did by taking the stimuli and response and looking at them in the original unit cell and in a symmetrically transformed unit cell, and we tried to get the property to be the same, and that gave us the property that symmetric second rank tensor properties are basically isotropic, because there also, remember, we used the symmetry property. We said xy should be equal to yx, but it happens to be minus yx, and that is the reason why xy yx terms became 0, the off diagonal terms became 0. So, symmetry is already assumed. Why these properties should be symmetric is an altogether different argument. We will not get into it now at this point, but it is an interesting argument by itself. But if you assume that we are looking at a symmetric second rank property, tensor property, material property tensor, then in cubic system it has isotropic symmetry. That you can prove 2 ways. One is by looking at the stimuli response, doing a coordinate transformation which is a symmetry transformation on the crystal and matching the properties. The second one is by looking at the representation of the property tensor, which is quadric, and this representation quadric, if you represent it in terms of its what is known as principal axis, that is, there are always 3 mutually perpendicular axes, in which if you take the x1, x2, x3, all the cross terms will go to 0. In such a representation, if you take, because that represents the property, now for a cubic system, that representation quadric should have the symmetry. Which symmetry? 4 3-fold axis. If you now demand that there should be 4 3-fold axis for a generic ellipsoid of that type, you notice that it already becomes a sphere, and the sphere will have the symmetry of isotropy. So, this is another way of proving that a symmetric second rank tensor is isotropic in cubic systems. Okay. It is isotropic in isotropic systems also, but what is more, it is isotropic even in cubic systems, which obeys Neumann principle. Neumann principle says that the property should have a symmetry which includes the point group symmetry. Isotropy certainly includes the cubic symmetry, so it is allowed. Whereas, for example, a tetragonal symmetry is not including the cubic symmetry, tetragonal is less than cubic symmetry. So, no property can have tetragonal symmetry in a cubic crystal, for example. So, that is the meaning of the Neumann principle. So, we will later see how these kind of properties, the information about the property tensors are helpful for us in defining certain material properties when we are dealing with phase field models. Thank you.